Good morning, all of you. My screen is visible. Anybody? Hello. Anybody is there?
Yes, sir, it is visible, sir.
Okay. Okay, see that remaining controllers in the introduction portion. We'll see next one is AC voltage controller. Then we'll move on to cycloconverter, then inverters, then advantage, disadvantage applications. So we'll close this today. You'll see that AC voltage controllers. The main function is it will convert fixed AC to the variable AC with constant frequency. That is the major important point is here frequency will not convert fixed AC to the variable AC with the constant frequency or a same frequency. And this consisting of two thyristors are in anti-parallel. Either no two ways are there. If the rating is low rating, then we can connect one triac directly instead of using two anti-parallel thyristors connected in anti-parallel. No, two thyristors are in anti-parallel. Instead of that, we can use directly one triac. So that is depends on application, and this will be widely used in the light control, speed control of fans, pumps. For the low rating applications we can use it. And this is the process actually. The input voltage and frequency. So this is a some single phase, let it be 220 volts 50 hertz supply, and it is given to the AC voltage controller, and that will convert variable voltage across the load at constant frequency. So that sentence is very important. Frequencies remains constant, whereas in the other case the frequency is going to be variable one. That is a cycloconverter case. It is a variable one, and there is a classifications are there. So here classifications based on the direction, or you can say that unidirectional AC voltage controller are also called as a half wave AC voltage controller. So this is the one classification. Unidirectional means only one half cycle is going to be controlled, and another one is a bidirectional or full wave AC voltage controller. So in this case, positive half cycle as well as the negative half cycle, both is going to be controlled. So in the first one, only one half cycle is going to be controlled. Second half cycle is means negative half cycle will not control. In that case, if you take that scenario, means one thyristor and one diode is required, because negative half cycle is not controlling. For the negative half cycle purpose, instead of using two anti-parallel thyristors, one we can use thyristor, another one you can use as a diode. So that we call it as a half wave AC voltage controller. Whereas full wave case, two thyristors are in anti-parallel. That is only the difference. Now I will show the circuit, simple circuit. You can see here, you can use directly as a supply also like this, instead of using transformer and all. Directly you can connect like this also. That is also fine. So now we can see this. There is a supply, and to control the output, I am using one is a thyristor, another one is a diode. Then operation is very simple. What will happen during positive half cycle? Which one is a forward bias? There is a phase and neutral. During positive half cycle, thyristor T1 is forward bias. Once thyristor is forward bias at an angle of alpha, while we are drawing the waveforms are very easy. I don't know, input will start. This is our input. And what is next I have to give? Firing pulse. At whatever instant you want to fire, you can provide as a firing pulse. Let it be, this is a pulse. Up to 5 you can give it, or spice just you can give only spike pulse, like that. And the same cycle is repeating. Here also firing pulse is required. This is a pulse for IG1, means thyristor gate signal. This is a supply. Again, all these things will come only for just understanding only. Now, for this one, I don't want to give the firing pulse because it is a diode. So that's why not required. If it is thyristor, during negative half cycle, this will be forward bias. I have to give the firing pulse here for the negative half cycle. So now, at moment, I don't want to give the pulse to the diode because it is not required. Whenever it is positive, it is going to conduct. Now what will happen, we can see that output voltage waveform I want to draw. How will you draw the output voltage waveform? Now, during positive cycle, it is forward bias at an angle of alpha. This is alpha. Giving pulse to the thyristor, it starts conducting. Output is same as the source. Now we can draw here. From here onwards, output is same as source. Over. Because before this 0 to alpha, thyristor is not conducting, output will be 0. And once thyristor is conducting, we are getting as a output same as source, because load is directly connected like this. No? Here one point, and it is goes like this, and it is connected here. So whatever source is there, load is directly connected to the source through thyristor T1. Then current is passing like this. This is the current direction. So load is directly connected to source. Now, due to natural commutation, thyristor is turn off at pi. Once thyristor is turn off at pi, then what will happen? This will be T1 is turn off at this instant. And negative half cycle from pi onwards, what will happen? Pi to 2 pi. What will happen? This will be forward bias because this is negative, this is Hello? Hello?
Yes, sir.
I'm audible? I think I left that class, no?
Yes, sir.
Just now or previously it is there?
Some 5 minutes, sir.
Okay, fine. But then nobody is called me, no? If something is happened, you must inform, no? How can I know? CR or anybody, just my number is there, no? You can call. Because I'm in the slide mode, I cannot observe whether I'm in there or not. So if anything is there, let me know. In between something may be happening. Okay. Now, I'm audible right now? Hello?
Yes, sir.
Yeah. So now you can see at pi, the thyristor T1 is going to be turned off. And what will happen? Why this gap is coming? That means my screen is
Sir, your
visible.
screen is not visible.
Yeah. I will share once again. My screen is visible now.
Yes, sir.
Yes, sir.
Okay. Now we'll see that bidirectional or full wave AC voltage controller input is AC supply, as such we can write, and we have to provide the firing pulses. Pulse must be 2 pulses here, one pulse per positive off cycle thyristor T1, another one at negative off cycle per thyristor T2. Like that we provide the firing pulses. Next operation, during positive off cycle we are giving, T1 will be forward bias, and we are giving pulse at T1. Then what will happen? It starts conducting. Even though if it is forward bias, if you not give the firing pulse, it won't conduct. But it will conduct only at alpha, because we are providing pulse at alpha. And the T1 will start conducting. If this is conducting, I want to measure voltage across the load. What is this? This is same as source only, because it is connected, load one end is connected directly to this point, other end is directly connected to the this point. So that means whatever source is there, same voltage applied across the load side. Similarly, during negative off cycle, what will happen? So during negative off cycle, this will be plus and this will be minus. Then thyristor T2 is a forward bias. The reason is, you can see, anode is connected to plus and cathode is connected to minus. Then what is the current direction? Start with plus, go like this, it goes like this. That's the reason you can see that there is a plus, and then load, it go to the T2, go to the minus. So now what will happen? Output same as the source only, but the current direction is opposite to the reference. That's why it will be negative. So now this is a voltage waveform. It started at alpha, same as source voltage. At pi, T1 is turn off due to natural commutation, but pi to pi plus alpha, no device will conduct. Reason is what? At pi, T1 is already turn off because due to natural commutation, and T2 is a forward bias, but no firing pulse at pi. Pulse is there only at pi plus alpha. This is the instant pi plus alpha, because this is a pi. You have to maintain alpha, positive cycle, whatever alpha, same alpha will be negative cycle for the T2. Now, at pi to pi plus alpha, no device will conduct, because one is already off, two is forward bias only but not conducting because no firing pulse from pi to pi plus alpha. Exactly at pi plus alpha, pulse is given to the T2. Then T2 will start conducting. Once T2 is conducting, then only you will get it a output same as the source in the negative direction. That's why from pi plus alpha onwards we are getting same as the source. Whatever source is here, that one. Whereas earlier also this one for positive. And again for positive cycle is going to repeat it. And here you can represent, we want to see the voltage across the device. You can represent, this is a current waveform, voltage waveform and current waveforms are same. That is the reason I drawn the exactly same, because it is a R load. And now for RL load case, it may continue to conduct some more time, that we'll see in the actual unit. At moment R load, voltage and currents are in phase. Whenever voltage is 0, current also will be 0. So only magnitude will reduce. And this is the thing for voltage across the device. Yesterday I mentioned one logic to represent voltage across the device. When the device is conducting, voltage across the device is 0. If device is open, voltage across the device is source. Same logic only. You can see from 0 to alpha, what will happen? No device is conducting. So that's why it is getting same as the source. And from alpha to pi, here T1 is conducting. So that's why I make it as a 0. I make it here also 0 for T2 thyristor also, because both are in parallel. That's why any one of the device is conducting, even though other device is open, but voltage across the device it measures same as this voltage only, or this is conducting, if you measure here same as this voltage only. That's why if both is conducting, voltage across the device will be 0. If any one is conducting also 0, no? Only one will conduct. If this is conducting 0 or this is conducting also 0, parallel. And if both is open, then only you will get it as a source. And this with respect to anode, this magnitude, and this with respect to anode, it is opposite, no? So, anti-parallel, no? That's why same magnitude, negative, like that. So this is the brief introduction about the AC voltage controller. Now we'll see the cycloconverters. What is the function of cycloconverter? It will convert. What is the difference you recall? Cycloconverter is convert AC to the variable AC only, but variable frequency. Here main intention is to get variable frequencies in the output side. That is the intention. But AC voltage controller intention is variable voltage only, but not variable frequency. So now function, you can see what is the function. It converts one frequency to other frequency, means variable frequency, that's all. So voltage also will vary, but major role is frequency varies. And then there is a line commutation is more common in these converters. But there is a one forced commutation also required for step up cycloconverter. For step down cycloconverter, line commutation or a natural commutation only. But for forced commutation, the device need to turn off forcibly before pi. That is the instant we require to get higher frequencies. That's why forced commutation is required. Slow speed and large AC drives, there is a some high rating applications only we are using as a this type of cycloconverters. And now we can see the classifications. Classifications are same, no? But based on the connection, we divide as a two classifications. One is a midpoint, another one is a center tap. So midpoint cycloconverter and center tapped cycloconverter. And here the cycloconverter classification based on the voltage, or I mean based on the frequency, we divide step down cycloconverter and step up cycloconverter. And again we can classify this in terms of connection wise. This is a rating wise, means frequency range wise. You can see that step down cycloconverter and step up cycloconverter. And based on the connection, you can say that midpoint and bridge type. For rectifier case also, we noticed one classification: midpoint rectifiers and bridge type rectifier. The difference between these two is there is a, in midpoint case we require as a transformer, whereas in the bridge type we don't require any transformer, directly we can give it. So then another difference also there, if I use midpoint, we require only less number of thyristors. Suppose in the case of rectifiers also, midpoint fully controlled rectifier we require 2 thyristors. Same fully controlled rectifier, if we go for bridge type, we require as a 4 thyristors. But the same output voltage, we don't get power or voltage, anything more. It will give same output voltage only. But the thing is, you can avoid the transformer. That is only the difference. In that wise, the midpoint and bridge configuration. So these are the classifications. I will explain briefly about any of the thing, whether it is a step up or a step down, or both. We will see that. The internal diagram we can represent like this: fixed voltage and fixed frequency AC input. That means some 230 volts 50 Hz supply. And what we can get it as a variable voltage and variable frequency. Both is possible in case of cycloconverter. And I told no, there is a 2 types: midpoint and bridge type. And another classification, step down and step up. So now I will show you midpoint step down cycloconverter and bridge type step down cycloconverter. Circuit different, but waveforms are same, because outputs are same, whether I can use bridge type or I can use as a midpoint type. Only thing is you can remove the transformer or eliminate the transformer. This is the circuit. Now in this circuit, transformer, midpoint transformer I use, and I am using as a 4 thyristors. And we'll see the output. This is the output. In detail explanation not required at moment, or otherwise also I will explain at moment, small thing. Here anybody can observe the waveform, forget about operation, all this thing. By seeing this operation or waveform, output waveform, the red line is your output voltage waveform, this one. So this thing is your output voltage waveform only, and I am taking average, I am getting this way. Or this one, 3 positive half cycles and 3 negative half cycles in the output. Now how much output frequency? Input frequency is 50 Hz, that is fixed one. What is the duration? We started here, we ended here. This frequency or time duration, I call it as a TS. TS is nothing but a 1 by Fs, or Fs is equal to 1 by Ts, anything. So this is known to you 1 by 50, means 0.02 something, and that is the time for input duration. But what about the output duration? Can you say what is the F out frequency from this? How much frequency is reducing? You can see this much time duration is the input and output is this much time duration. So output time is more. How many times? 3 times. See that? 1, 2, 3. So 3 times output time duration is more. Then automatically, if denominator is more, 3 times of the source time, then your frequency also decreased by 3 times. You can see that F out is equal to 3 times will be more Fs by 3. This is the reason. If time duration is increased by 3 times, then automatically frequency is decreased by 3 times. That is the reason we are getting as a higher time duration and less frequency. Suppose the question they ask in an exam, show that output frequency is a 4 times of the input frequency. What is the modification I need to do in the waveform? We need to represent, instead of 3 cycles in the positive, you make it 4 cycles in the positive and another cycle is in the negative. So 4 cycles are in positive, 4 cycles are in negative. Then your time duration will be increased by 4 times. Then frequency will be decreased by 4 times. So now F out is equal to Fs by 4. That is the way, and how we will get positive cycle or negative cycle also very simple. I will explain that small thing. Now first we will see the positive cycle. So this is the positive. Positive cycle, what are the devices are forward bias? This is a plus, this is a minus. Whenever anode is positive with respect to cathode, it is a forward bias. Now you can see plus is connected to here, T1 is forward bias. Minus is connected to here, T4 is forward bias. That's all. And that is your choice whether I want to give firing pulse to the T1 or T4. If I give pulse to the T1, T1 will conduct. Or if I give pulse to the T4, T4 will conduct. We don't require to give pulse to both the device. I want only any one has to conduct at this moment. Now current is passing like this, it is goes like this. This is your reference, and reference current and actual current is same direction. That's why you will get positive. So at an angle of 0, let's assume that if I start at 0, we can directly getting output voltage by firing as a T1. Suppose instead of T1 if I fire to I am giving pulse to the T4, then what will happen? This is minus, this is plus, minus plus, then current will pass like this. Now it is opposite direction to the reference, we will get as a negative voltage. Instead of getting positive, you will get like this. So from this it is very clear, based on our requirement, you just fire the corresponding device. Whenever during positive of cycle, if I want positive, you fire the T1. During positive of cycle, if you want negative, you fire the T4. See that here is a positive of cycle, but what I want negative. So what I want to do, instead of firing T1, you fire the T4, you will get negative. So like that, at any instant you want to fire, you can fire that corresponding. Similarly, negative of cycle, this is minus, this is plus. Negative of cycle T3 is forward bias, T2 is forward bias. If I fire the T2, then what will happen? It goes like this, same direction. So that is a positive. And if I fire the T3, it goes like this, opposite direction. You can represent it go like this, no, opposite direction, you get negative. So again, in the negative of cycle, if you want positive, you fire the positive group device, and if you want negative, you fire the negative group device. That's it. So whenever I want positive, you fire the T2. If I want negative, we fire the T3 over. That's all. That's why I mentioned here numbering also. To get positive, I fire the T1. To get positive but negative off cycle, I fire the T2. And positive off cycle, positive I need PT1. And negative off cycle, negative is required. T3 will fire like that. So only thing is, you identify which device is forward bias at what instant, If I fire that device, what you will get? If I fire the T1, I will get positive. If I fire the T4, will get negative. But whereas in negative half cycle case, this one. If I fire the T2, will get positive. Fire the T3, will get as a negative, like this. So that is the way you will get it. Now frequency is going to be vary, and we are allowing to conduct the device up to pi. That's why it is a natural commutation. We are not turn off in between. I am allowing the device to conduct up to pi. That's why it is a natural commutation. Same step up also. Only thing is forced commutation is required. So now this is the waveform. The difference is very simple. Whereas earlier, to get output voltage waveform, I make use of many number of input voltage waveforms. Here, to get one input, this is one input. How many outputs I got? This is one cycle, means positive and negative. Then another cycle, positive and negative, 2. And this is 3, positive and negative, and then 4. So one full cycle of a AC supply, I am getting 4 cycles in the output. So that is the reason you can say this is output frequency is 4 times. And same operation for positive P1, T1 and negative T4, again for negative half cycle positive T3, negative T2 only. But earlier we allow the device to conduct up to the pi. For once T1 is conducting, the device is going to conduct up to the pi. But now if I allow the device to conduct up to pi, I will not get this many cycles within the half cycle. You can see this is only one half cycle, but I am getting 2 cycles in the output. Then at once this point reaches, if I am allowing T1 to conduct first, this is the output, first envelope, let it be, this is the output. For T1 is conducting, this is a T1 is conducting. If I am not do anything, it go on conduct up to the pi. But I don't want to allow them to conduct up to the pi, because I need negative half cycle immediately after some time. So once it is conducting, we don't have any provision to turn off until unless if we apply forced commutation. That's why what we'll do is apply the forced commutation at T1 instant, at this instant, and forcibly turn off the device. And what will happen? And they give the pulse to the T4. So then once if you turn off the device and T4 is conducting, will get as a negative. So negative half cycle will be obtained. Again forcibly turn off the T4 and give the pulse to the T1. This much duration. Again you turn off the T1, give the pulse to the T4. Like that, forcibly you have to turn off the device. Both T1 and T4 is able to conduct up to the pi if you not do anything, because both are in forward bias. If I give pulse to the T1, it will conduct up to pi like a step down. But now what will happen? Output frequency time duration is very small, 4 times are small when compared to this. Then what will happen? Then this is one cycle, then second cycle, then third, fourth, like that. Negative half cycle also you operate T3 and T2, you will get it as another cycles. So with that we can able to get it as a output frequency will be higher by applying forced commutation. Similarly, instead of using this type of circuit, you can use this is the circuit. Again waveform is same only thing is conduction devices are different with respect to positive half cycle and with respect to negative half cycle. This is the bridge type. Now remember, your waveform is same, but if I use the transformer, I am using only 4 thyristors to get this waveform. But to get same waveform, what I did is I used as a bridge type. Output is same, but I used as a 8 devices. Only thing is advantage is we are not using the center tap transformer. That is the advantage. In addition to that, we are using as a more number of thyristors. So this is the step up and step down cycle converter. Now last one we'll see the inverters. What is the function of inverter, anybody? See, the all 5 functions must remember. With that line, the inverter, it will convert DC to AC. Fixed DC given to the inverter, it will give as a variable AC by make use of a control strategy. There is an internal control strategy as well as the external control strategy. So now that is the main function of inverter. What is the first thing? It converts AC to, DC to AC. Means DC is a fixed DC and AC is a variable. Even though if you use the appropriate control strategy, you can get to variable frequencies also based on the pulse width modulation technique and all. You can get it as a variable frequency. But here you can see that there is a variable voltage, we can get it, or both you can get it based on your control strategy. And the next point you can see that use line or forced commutation. Line commutation will be used only in the case of rectifier if alpha greater than 90 degree. The mode we noticed in that introduction class, there is a, you can see the graph something like this, 2 quadrant operation. This is alpha is less than 90 and this alpha is greater than 90. So in that case what will happen, voltage is negative but current is positive. Current is positive. So voltage is negative, current is positive. What will happen? Power? Power is negative. Power is negative means it will flows from load to the source. What is load? This side is a load in the rectifier I am telling. And this side is a source. So load is a DC in the rectifier and power flows from DC to AC. Then this I call it as a inverter mode of operation. Even though if you are using as a rectifier circuit, but if you make it alpha greater than 90 degrees, that will act as a 4th quadrant operation. Whatever kinetic energy is stored in a machine, that will convert back to the AC. That's why I call it as a line commutated inverter. Operation is inverter operation, but commutation is a the terminals are connected to AC. Because of the AC supply lines, we make use to turn off the devices. That's why we call it as a line commutated inverter. And in general, in this unit, we will use only the forced commutated circuits. So input is fixed DC. I'm operating as inverter. To turn off the inverter, we require as some forced commutation circuit. And this will be used in the induction motor speed control, synchronous motors, uninterruptible power supply, and HVDC transmission. What is the meaning of HVDC transmission? There is high voltage DC transmission. Here the major important, there is a AC side input is AC supply, and then there is a substation convert AC to DC, then it is transmitting, then in the end side again we need AC, that's why the receiving end station that will convert DC to AC, that is a inversion mode of operation. So 2 stations are there in HVDC. One is a rectifier station, another one is an inverter station. In that also we required as a inverter. And this you can see that in the general case, in the inverter, so preferably we don't use the SCRs. For that commutation circuit is complicated. That's why we are using as a gate turn off thyristors. So GTOs, gate turn off thyristor, automatically the device itself is going to be turn off that is one of the latest advanced devices. GTOs will be used, even though there is a MOSFET IGBTs are using, but still G2O is a preferable one for high power applications. These are the some of the points in the inverter. Now we'll see the classifications of the inverter. What are the classifications in this case? There is a series inverter and parallel inverters and all is there. That's old method. That's why generally we didn't use that in the syllabus. But in the bridge inverters only we are using. In a bridge inverter, we classified that. What are the classifications? Single phase inverter and three phase inverter. What is the difference in these two? Again, same as in the rectifier classification. Single phase rectifiers and three phase rectifier. If input is AC, we are using as a rectifier. Here input is DC, but inverter output side, if output is a small amount you want, you can use as a single phase inverter, or the load is a high load, high range of load, you can use as a three phase inverter. So that means single phase inverter and three phase inverters will use. And in the single phase, you can see that half bridge inverter and full bridge inverter. So two type, like a half wave AC voltage controller and full wave AC voltage controller. Here also there is a half bridge inverter and full bridge inverter. Here in the half bridge inverter, you are getting output is half of the input, whereas in full bridge inverter you are getting as a full output in the load side. So load is connected as a AC. Same scenario for three phase, but here three phase there is a mode of operation, how the device or the circuit is going to conduct operation of the circuit. So there is a totally 3 plus 3 6 devices are there in the three phase inverter, and here the single phase full bridge inverter we have only 4 devices, and there we have as a 6 devices are there to operate as a three phase mode. In that input is DC, it won't be affect anything. Only thing is output side, the connection, instead of 2 legs you make use of a 3 legs. That means each leg will give as a one phase to the load side, and that you can connect it to the three phase induction motor or something like that. So in this mode there is a 120-degree mode of operation and 180-degree mode of operation. What is the difference is, in 120 degrees mode of operation only 2 devices will connect at a time. In 180-degree mode of operation 3 devices will connect at a time. So like that, the firing pulse duration, if you give firing pulse up to 180 degrees, it will operate as a 180-degree mode of operation, or else if you give only 120 degree, then the device will conduct only 2 devices. There 2 device and 3 device combination is there, but here we are using as a only 2 device, one is upper, another one is a lower, like that. So these are the some of the classifications of a inverter. Now you can see this is a half bridge inverter. I will explain directly RL load. RL case, what will happen? Some energy stored in inductor. That energy has to be dissipated through feedback diodes. Here you can see the circuit. Normally half bridge inverter means one leg. This combined we call it as a one leg, anti-parallel diodes. This way also you can represent, instead of separately draw the leg. This is a anti-parallel diode. That's all. So only one. Now latest devices, IGBT and all, if you use inbuilt switch, this one we call it as a switch, and this is a diode. So inbuilt will represent that diodes nowadays devices. Now we'll see the operation. Just see how that is going. First supply, here half of the supply we need to give, half bridge inverter, midpoint DC is required. So initially thyristor S1 or T1, whatever notation you follow, switch 1, switch 2 or thyristor T1 and T2, that way also correct. And now whenever supply is connected to the S1, then what will happen? S1 will conduct. Supply is given and pulse is given to the S1 and thyristor T1 is conducting, current is passing through like this. Whatever this red ball is moving, no? This way we are getting as a positive way. So it starts Vs by 2 and it goes to the S1 and then load. So the current direction is, and you can see the load current direction is this one, and then it is passing in the same direction and it will be the positive. And voltage across the load if we measure same as this, because it is connected only Vs by 2. And next, during that instant, some energy stored in inductor, that energy has to be dissipated. So in that in detail explanation will come in the corresponding circuit on this inductor. If I place as in series with that resistor and inductor, this is the load, let us assume that. When the previous instant current is passing like this, it will store the energy, plus and minus. And once the device is open, applying forced commutation, S1 is open, then whatever energy stored in that is going to dissipated in this mode, because polarities will reverse while it is back EMF is change the direction, then the plus, then what is the direction? Current, it goes to the source and it goes to the D2 to out. This is the direction. Then what will happen if it is passing like this? S2 I am not giving pulse, only diode is forward biased and reveals that energy. Whatever energy is stored in an inductor, that energy is going to be reveals. If this energy is completely dissipated, then what will happen? This device will be turned off. No energy in the inductor, so automatically current will be 0 and diode will be D2 will be open. So S1 is open, now D2 will open. At that instant you can fire the pulse to the S2. So that's why I given as animated. Now we can see if that energy is dissipated completely, this will be open. Now lower group device S2 is connected to the Vs by 2 plus, it is a forward bias at an angle of alpha giving pulse to this, then this is conducting. Then inductor is storing energy, you can see this, it is storing energy in this direction because current is passing like this, no, plus and minus. Once the time is over, means we will decide the time when it has how much duration it is conducting S1 and S2. The rest of diodes will be dissipation only. Now it is conducting energy stored will be like. While it is turn off the S2, the dissipation will reverse. This is your dissipation. And now which one is forward bias? Plus is connected to D1. So therefore D1 is going to fire and current is passing like this. This is internal loop. And with that you can able to operate your now see that once S2 also open, whatever energy stored in inductor, it goes to the D1, it goes to the source, upper of the source. So this way we can operate. Once energy is completely dissipated, all the devices will be open. Again, if you fire the T1, output will be Vs by 2 and then inductor will store the energy, and then once T1 or S1 is off, you have to fire the automatically D2 will conduct like that. All the sequence will repeat. This is the waveform giving as a firing pulse. This is the all the things we need to do in lab. And this is the firing pulse to Ig1 and pulse to Ig2. Ensure that S1 and S2 should not fire at the same time. If pulse is available for S1, S2 will be off. S2 pulse is available, S1 must be off, like that. So what will happen if I give pulse to both of S1 and S2 at the same time? The reason is straightforward. We can see here Yeah, this one. These two are in the same leg. If S1 is conducting and also S2 is conducting, if both is conducting, what will happen? If this is conducting, this leg will be short circuited. If this leg is short, automatically supply is short circuited. That is the reason you can see that both S1 and S2 should not fire at the same time. So that is only different. Now that way we are providing pulse. As I said, if S1 is conducting, output half of that, that is what Vs by 2, and S2 is conducting, output is half of that, Vs by 2. So this is the voltage waveform. And current waveform, I told no, it is increasing. If this T1 is conducting, D2 will fire and D2 will be dissipation mode, positive only, but whatever energy stored in that inductor, that is going to be dissipated. That's why current will be decreasing. Again at this point, even though pulse is available, if D2 is conducting, that makes reverse bias the T2, and once D2 also turn off, then T2 will fire. Like that, I mention every instant. And again I will explain at the time of inverter experiment. So you don't worry in this regard, just how the operation is going to be. Exactly same operation for full bridge inverter also. Only thing is different here. Instead of Vs by 2, if I operate full bridge inverter, we'll get it as a Vs. Instead of minus Vs by 2, you will get it as a minus Vs. That's all the difference. And here only one leg is there. There is a two legs will be there. Each leg will conduct one device. That's why conduction of devices here, instead of T1, it will make it T1 and T2, both will conduct, and this will be D3 and D4, like that. So I will show that. This is the full bridge inverter. Now remember the circuit difference. What is the circuit difference? Once if you see the half bridge inverter circuit and full bridge inverter circuit, there is a small difference. Supply is one different. Instead of using Vs by 2 and Vs by 2, midpoint DC is required for half bridge inverter. That is one of the drawback. Another drawback, we are getting output only Vs by 2. That is half of the input only we are getting. Input is total Vs, no? Vs by 2 plus Vs by 2, total Vs is there. But output you are getting only Vs by 2. That is, these are the two reasons we are not using full bridge, half bridge inverter in that. But now, if I use this way circuit, exactly same circuit, nothing is there, only I taken one more leg. Earlier it is there like this, so two thyristors, two diodes, no? Same setup, I replaced one more here. That will become as a full bridge inverter. And now here you can see that if supply is given and then firing pulse is given at the same instant, supply and pulse is given. For this case, T1, T3 should not fire at the same time. T4, T2 should not fire at the same time because both are in the same leg. That's why T1, T2 will not fire at the same time. T2, T3 will not fire at the same time. Like that, you provide the firing pulse to the T1 and also pulse to the T2. So if both these turn on, then what will happen? Current will pass like this. That's all. So now it is using the devices T1 and T2. Only for negative off cycle, these two devices is going to fire. So like that, once negative off cycle, the whatever energy stored in that, it is goes to the not negative off cycle. There is a off duration. Here I call it as a on duration and off duration. This is for T1 and T2. This is for T3 and T4. So now once pulse is given to the T3 and T4, then what will happen? Current will pass like this. It goes T4, goes like this, T3 to out. So this way we are getting. This is the current direction for T3 and T4 is conducted. Similarly, current direction for T1 and T2 is conducting T1 and then T2 to out. So with this we can able to get it as a output voltage same as the source voltage. And now you can see how it is going to be operate. Initially T1, T2 is conducting. Now inductive load. For resistive load case, diodes are not into picture. Whatever T1, T2 is there, if on duration is over, T3, T4 will fire. That's all. But now RL load case, inductor will store some energy to dissipate that. It has to fire the T4 and D3 and D4. Now we'll see carefully how that line is moving current direction. And after some time, whatever on duration is over, I apply the forced commutation, I turn off the T1 and T2. Then what will happen? T1, T2 will off. And diodes D1, D3, D4 is going to be on to dissipate that energy. Again, after some time, if energy is completely dissipated, no current pass through the diode D3 and D4. If no current pass through the diode, the devices will open. Now after some time it is also open. Now I am giving pulse to the T4 and T3. So the current is passing through T3 and T4. Then immediately there is a diodes will forward bias to dissipate that energy. Here diodes are D1 and D2. So like that you will get it all the devices conduction, whether it is a diodes or a thyristors, and that is the output waveform. You see that advantages of power electronics. There is a lot more advantages are there. I will show one by one. There is a high efficiency as there are less losses in a device. Why it is high efficiency? Because device losses are minimum, no rotating parts. So that is the reason very high efficiency is possible. And reliability also. Device failures are very minimum. It won't be happen any failure. That's why reliability also will be high. Another one is long life with less maintenance. So these options of moving parts. So only device, the rating may be very high. Each device switches. Here only we are using switches, MOSFET, IGBT, BJT, SCRs, and some commutation circuit L and C. That's all. No other devices are required. And firing circuit. There also we are using as a some programming. Nowadays we are using directly programming to generate the firing pulses. All these things. And now this is a long life with less maintenance and fast dynamic response. Once if we change the alpha some one value to another value, immediately response also going to be changed. So that is the reason we can say that fast dynamic response also there. Another one is a lower cost. So cost will be very cheaper even for IGBT and all 400 or 500 rupees only. So it not be much cost, very cheaper. And then flexibility in the operation. Simple operation by generate the firing pulse. So once if the device is forward biased, if pulse is there, automatically device is going to be conduct. So that is the simple way of this advantages. Now we'll see the disadvantages. Only major disadvantage harmonic generation. So once the power electronic circuit semiconductor devices if I use, automatically a lot of harmonic is going to be generated. For that performance will be little bit less because of the harmonic, and to overcome that we need to filter out that harmonics. So we have to use as a filtering requirement. And here certain converters like AC to DC or DC to AC and some certain operations, there is a low input power factor also will be there. By using the freewheeling diode and all it will improve, but to improving power factor another aspect is one of the drawback. And the regeneration of power is difficult, and because once the device is unidirectional device, if you use power flows from load to the source is complicated. So that type of regeneration, because in normal case regeneration action power flows from source to load to the source, there somebody else has to utilize that power. And this cost of the converters is high. Once if you are overloading capacity you want to increase, that overload capacity is very small in the device. Whatever ratings are there, it will operate. You cannot use 3 ampere thyristor to something else cannot be used. That is the reason. These are the some of the drawbacks. Applications, many applications are there. Power electronic, renewable energy side, industry side, and utility systems, and electric drives, whether it is AC or DC, power supplies and power system application. All these applications are there. You can see that individual residential application, light control, cooking and viewing machine, and entertain equipment, TVR, washing machine, mixes, everything. Lot of fridge and many air conditioner nowadays. IoT based air conditions also there. Vacuum cleaners, so dryers, so like that. In any, even if you go to industry application, electric drives, it means DC motor, AC motor, this machine tools and arc furnaces, ovens, grinders, mixes, and then commercial applications also there. Fans, elevators, like this, many industrial application, and transport also there. And another one is power system application, HVDC transmission, fax controllers, means TCR, thyristor control reactor, and switched control compensation, like all fax controller equipment. So many cases we are using as a power electronic equipment. So these are the aerospace applications also we are using this power electronic control strategy. So these are all about basic introduction of a power electronics. Now the next class onwards we'll start with normal subject. So that will start with thyristor first, and then we'll move on to BJT, MOSFET, IGBT and all. So if you have any doubt, you can ask me. Otherwise you can leave. So we'll download the attendance. And I uploaded that material in the LMS portal, whatever PPTs I am covering, but don't share to anybody else. Without my permission, if anybody asks this material, other colleges or anywhere, you don't share. You just utilize yourself, because it is whatever I am explaining, I prepared the PPT, but somebody's explanation is different, and if you give this PPT, they will confuse. Not only this introduction portion, lot more coming. I will give all the things, even without using textbooks also, this is sufficient, but still you don't forward this to anybody else, PPTs. It is strictly for our students.